Hello, we have a short chapter about equilibrium. You will see equilibrium in a lot of different questions. However, equilibrium itself, tested in a discrete question, is very unlikely. Most likely, you'll see as part of a passage prompt asking you where this reaction will proceed if you were to do a certain condition, such as adding more heat, adding more of this reactant, or decreasing some reactant. Or perhaps you might see it in a biological question where, oh, this inhibitor was added, and according to the Le Chatelier's principle, what will be the resulting effects on a person, right? And you have to draw some influence from whether it decreases the overall efficacy of the drug because there's less of it, or the Le Chatelier's principle shifts it closer to producing more. You'll have to see, but equilibrium itself will seldomly be tested as a own discrete question. So here we go. Law of mass action describes how the general equilibrium is describing the forward reaction, as we saw in the previous chemokinetics. The forward rate is K times AB to a certain constant, and that goes for forward and reverse reaction. So if we were to go forward and reverse and do cross multiplication, we can see that when we rearrange it, Kf over Kr, we can use that as the equilibrium, and if they're to a certain constant that they're in dynamic equilibrium, the forward rate versus the reverse rate is equal, or to their respective amounts, then we can get using the molar equivalence and the ratio of the products and the reactants as well as their coefficients to find out about the equilibrium. So both of C and D are the products, and A and B are the reactants. Their concentration is off to a certain degree based on their coefficient. Note, the higher coefficient something is, the more you'll have to add onto the top exponent, because they're going by that additional order, right? So for every one of them you produce like a square of them. Now, we also have this Q, which reminds us of evaluate at that point in time whether it is greater or less of the equilibrium constant. If Q at this point in time is less than the equilibrium constant, that means A and B, the reactants, are more than the top, right? If you know fraction, right? The denominator is more, that means it's less than 1, or less than whatever equilibrium constant was. So that means it's bottom heavy, and it will attempt to shift right in accordance to the Chatelier's principle. The Chatelier's principle basically says that if you add more to the reactants, more products is going to be made to make it equilibrize, right? If you add more ice to hot water, the more of it is going to melt out. If you pour more cereal in milk, you will have to eat more cereal. I don't know. But anyway, if Q equals K equilibrium at this point in time, then, well, it's not going to go anywhere. The Gibbs free energy is 0 because it's not going to shift left or right in a particular manner. It's going forward and reverse at the equal amount rate. If Q is bigger, that means it's top heavy. There's more products and reactants. Well, in an attempt to dissolve that, the product is going to make more of the reactants. So it's going to shift to the left, okay, to try to get to that K equilibrium. Now, we have a common question that will be asked, and this is the one that will likely come up if it ever comes up as a discrete question, where it gives you a certain amount of product or amount of reactant and its concentration, or you could solve for its concentration and said that is left in a container and there's a certain amount of it being dissolved, let's say X, and when that forms a product, the product has a certain coefficient to it, and you will have to work out the K equilibrium constant for that, find the equation, and you will just need to determine how much product is being made from the reactant you put in to let it react naturally. You could see this, or you could see an ICE table, which is initial change versus the expected results. So we have 2b because we have 2 of the x being made concurrently, and squaring it. So if you want to find out the total amount of product being made, you just take the 2x. But if you want to find out the individual amount, then it's just the x without the coefficient. But typically, you will need to get the 2x as a compound whole if you want to answer how much product is made in concentration-wise. And from initial, we know x is a lot smaller than A initial. If A initial was like 1 mole or 2 molar, and x is very, very small. That's how we know if a KEQ is very, very small, like 10 to the power of negative 12. That would be extremely small, much smaller than the molar mass A. Then we can justify removing x from here because it's negligible, and then multiply it by A, and then we just divide that. We root that and then divide that by 2. Simple. Okay. Next is just the Chanteloup principle. If we have A and B here, since there's more compounds or more molecules here on the A side, reactant side, than the B side, if we add more pressure to it, the high pressurized molecules want to shift more to make more products to relieve the pressure. If we decrease the volume, it wants to make more of A to increase the pressure. If we increase the amount of A, it's going to shift to the right. If we increase the amount of B, it's going to shift to the left. If we reduce the heat, it's also going to shift to the right to make more heat. It's like after you take a whiz, you do a little shiver because your body loses some heat temperature, so you want to recover some of that by shivering. Low temperature kinetic product, and high temperature makes thermal product. In a chemical reaction, there's the activation energy and makes the product, overall product, right? The kinetic product is formed when there's less energy involved and it can be formed faster. Sorry about that. And the thermal product is when there's more energy available to do it. So for instance, you were given 10 seconds to draw a picture of a banana, right? And 10 seconds to do it, scribble really fast. But if you were given 100 seconds to draw a banana, it will have a lot more detail and generally just a lot more appealing, right? That's the same thing here in chemical reaction. Kinetic product is a lot less appealing, but it can be formed very easily. You get the idea, but it's less stable. Thermal product requires more time, requires more energy, and it's more thermodynamically stable. The steric bond is hard to get into, but once it's there, it's more stable. And that's pretty much it for Le Chanteleur's principle and equilibrium.